In finance and forecasting, we lean on models to make predictions, but models are just abstractions, simplified stand-ins for reality. What happens when their promise, like 95% confidence intervals, don't hold up? When attempting predictions, one often has to fit a model to data and then use it to guess future values. Given the reliance on models, it is worth taking some time to explain what a model is, in general, in practice, and what it produces. In general, a model is a representation of a system created by abstraction, i.e., stripping away all irrelevant features. In practice, models take the form of mathematical formulas, algorithms, or code that relate observations and known quantities to non-directly observable variables of interest. As an example, consider the following curve fitted to the data. Real models are rarely this clean. We will consider the SARIMA model fitted to historical egg price data from the Fred database. This model produces not only a point estimate, but also a confidence interval as predictions. Before we proceed, we must first define what confidence intervals are and how they are computed, as they are often misinterpreted, leading to overconfidence. A confidence interval is a range of values associated with a level used to estimate an unknown statistical parameter. Mathematically, you can think of it as the following range defined here, where we claim the probability that our estimated variable falls in this range is 95%. First of all, confidence intervals are used in the estimation of fixed yet unknown parameters. Assuming that the sample was randomly taken from some distribution, it is a fundamentally different question from asking, given the model and the data that we do have, what range of values do we believe will contain the future realized value with 95% certainty? An interval that would answer the previous question is called a prediction interval. In our example, by performing a walk-forward validation of the model, we observe that the realized values exceed the 95% confidence interval approximately 15% of the time. We are now at a fork in the road where we have to decide between 1. Disregarding confidence intervals and looking for a prediction interval based option, possibly involving a ground-up reworking of the model. Option 2. Taking the confidence interval as a starting point and then trying to calculate how much we should trust it in response to the validation results. The former option is the superior choice, as it discards erroneous assumptions and produces results in line with our prediction objectives. However, the latter is often favored in industry because confidence intervals are ubiquitous due to institutional inertia, and patching symptoms is faster than solving root causes. In a perfect world, we would choose the first option 9 out of 10 times, but this is not a perfect world, and you may find yourself coerced by managerial forces to sacrifice strategy for expedience. Going with the second option, we use Bayes to compute how often we expect the CI to contain the true realized value, given that we have observed it not doing so in 82 out of the 542 predictions. Modeling the misprediction rate P as a beta distribution, we get the following expectation. Thus, we update our belief in our model's predictive power by not taking the 95% confidence interval at face value, but rather seeing it as an 85% confidence interval based on the walk-forward validation we have performed. If you are tired of pretending your model is right because the box says 95%, let the math merc recalibrate your reality.